The purpose of this video is to give an overview of the concepts of overburden, pore pressure, and fracture pressure, and share my understanding and lessons learned on these topics. These are fundamental concepts to drilling, and it is my desire that you will be able to understand these concepts and make good estimates of them in order to make good drilling decisions in well design and execution. Your comments and suggestions, as well as questions, are welcomed. My contact information is listed in the notes. Google Drive links to both the copy of the notes along with the link to the borehole fracture gradient model that we will be discussing are also listed there in the notes. In order to conduct this overview of these concepts, I have created these notes, which has some explanations, some diagrams, and also some application exercises that we will use in this discussion. You see there in the top of the notes, it has my contact information as well to the link of these notes, and also a link to the spreadsheet of the borehole fracture gradient model that I will be discussing. A more detailed outline of this agenda is listed there near the bottom, just for your information that you can go to later if you would like to. Having knowledge of the fundamentals of the earth and rock strength is paramount to drilling. Drilling a well requires us to drill through the earth, so it's pretty important that we have a basic understanding of the earth and some principles about earth's measurement and strength. The skill set to estimate overburden, pore pressure, and fracture gradients based on formation types is vital to choosing casing setting depths, determining casing pressure loads, testing and analyzing barriers, and doing well control assessments. Drilling engineers should be competent in obtaining reasonable estimates of these values for the areas that they are working. Not all drilling engineers took geology courses on these topics as a result of their college majors, or have had on-the-job training and experience in these just due to the place where they were working. So understanding these principles are especially important for the more difficult drilling environments. These topics are often avoided or not emphasized in many drilling training courses, which, if not understood, can lead to some faulty designs and execution plans. An introductory application question of some information that would probably be required and needed for the understanding of the integrity of a well might be this question that I have created as to illustrate. A well is being planned in the Gulf of Mexico with no near surface salt. What would be the estimated shoe fracture gradient and a shell formation at 10,000 feet on the well being planned in 7,000 foot water depth, in which the expected formation pore pressure is 9.5 pounds per gallon? And then, if a sand is present 50 feet below that casing shoe in the same pore pressure environment, what would be the expected estimated sand fracture gradient? If you don't consider yourself knowledgeable to assess the solution to this well-designed questions, then this video and material should be able to aid and help you in your understanding. The first section that we're going to go over is just going to talk about some natural properties of materials and common oil field conversion units and factors. Most of these are givens and a compilation of the properties of natural materials or unit conversions based on usage. Some volume units that we use in the oil and gas industry here in the U.S. is we use the gallon. So drillers deal with pump output in gallons per minute. We also deal with mud weight in pounds per gallon. We also use cubic feet as a volume. So cementers typically will calculate slurry volume in cubic feet of slurry volume. And then in production operations, we use a volume unit of barrel, which for barrels of production per day. And then likewise on our morning reports, we'll use whole volume in barrels, which seems a little bit confusion. You know, we are the U.S. oil and gas industry, and we're using 3 different volumes on our morning report to conducting our operations, which, you know, it makes it a little bit more difficult, especially when you're explaining this to people who come from different parts of the world and are not used to using 3 different volumes to do their work in. Some common conversion units and natural properties are the cubic foot equals 7.48 gallons. So if you wanted to go from gallons to cubic foot, you would use this conversion factor. A barrel is equal to 42 gallons, which is also 5.615 cubic feet. The density equals mass divided by volume, which is normally thought of as weight per volume in the Earth's gravitational field. So that's where we operate, so we can actually just think of it as weight divided by volume in our rig operations. Specific gravity for solids and liquids is a ratio of the density of a substance divided by the density of fresh water. A long time ago, the specific gravity of fresh water was defined as being a value of 1. It's one of the most common substances we have around on the Earth. So specific gravity of fresh water is 1, and its natural density, or weight, is 8.33 pounds per gallon. So seawater, which there's a lot of seawater obviously around all the continents, the density is about 8.6 pounds per gallon due to the salinity content of seawater. So its specific gravity would be the ratio of 8.6 for seawater divided by fresh water, 8.33, or would be 1.032. Formation water is the density value of salt water in the pore spaces, and it's generally used as a value of 9 pounds per gallon in the offshore environment, which is higher than the seawater due to the increased temperature and solubility of salt at the higher temperatures. So if we wanted to calculate the specific gravity of the brine that's in the pore spaces, we would use 9 divided by 8.33, and that would be a value of about 1.08. The value in the middle of continents, far away from the seacoast, may be a value closer to 8.3 pounds per gallon, which is the gradient of fresh water. It is based on the geological setting, and it is something that would be a local knowledge of the operating area. Now, rock, if we think about sand and clay particles from a driller's perspective, we can just use the specific gravity value of 2.65. It's not exactly 2.65. It varies a little bit, but it's close enough for doing our work. So the density of rock particles would be 2.65 times 8.33 if we put it in terms of pounds per gallon, which would be 22 pounds per gallon. So rock particles are 2.65 times heavier than fresh water, and this value will be used to approximate the weight of rock to evaluate our estimates utilized in well design today. Now, salt has a specific gravity of 2.15, which equals 17.9 pounds per gallon. And salt occurs commonly in nature in many structures and layers as 100% salt containing no porosity. So salt also has a very high creep rate, or ability to move based on increase in temperature. And that's the reason around continental shelves where you have large salt layers, you may have salt domes and things that were created because of this creep rate at high temperatures. Now, cement, I've just listed them there for your information, has a specific gravity of 3.16. Steel is about specific gravity of 7.86. and then brass has a specific gravity of 8.56. The next topic that we are going to be discussing is porosity. In order to illustrate porosity, I have made a box that illustrates porosity. For this example, I made a box out of plexiglass that is the width of 2 spheres. And so in this case, I have 8 spheres located in this box. These spheres are located on top of one another, so that's called cubic packing. We'll talk about that in a minute. But also the pore space is actually this space that's in between the particles. This pore space, we normally represent it as porosity, which is the percent of the pore space compared to the total volume of this box. So that would be porosity. This porosity in the reservoir or in the formation is always filled with one of 3 fluids. It's always gas, oil, or water. We're going to calculate for this example the porosity for this example in just a few minutes. But this concept of porosity is very important because this is where our oil or gas is stored that we're looking for when we drill an oil and gas well. Now, porosity is the pore space between the grains of rock in a formation. It's normally expressed as a percent of the bulk volume of rock, and it can be represented by the following. Porosity is equal to the pore volume divided by the total volume. Now, pore volume, is going to be the total volume minus the rock volume. So a lot of times we can't calculate the pore volume directly, but we do know it's going to be the total volume minus the rock volume. So therefore, if we put these two together, then the porosity is going to be equal to the total volume minus the rock volume, which is the pore volume, divided by the total volume. Now, the uppermost limit for porosity is cubic packing. So if we look at a diagram of cubic packing, it's the example that I made up with the little box that I constructed in my garage using 8 spheres. And in cubic packing, the spheres are directly on top of one another. So that's the first application exercise that we're going to do is based on these formulas that I've just described for porosity and the fact that you know that for this system that I have created, the radius is 4 times, in other words, the size of this box is 4 times the radius of these spheres, and it has 8 spheres in it. See if you can, I would pause the video and see if you can calculate the porosity up to the red line there based on 8 spheres in a box. Well, I hope you are able to do that exercise, and I think it would be very good if you did. So in order to calculate the porosity in the pore spaces, porosity is equal to pore space volume over total volume. The pore volume is equal to the total volume minus the rock volume. So therefore, again, porosity is equal to the volume of the box minus the volume of the spheres divided by the volume of the box. So the volume of the box, since we have a width and a depth and a height of 4 times the radius of a sphere, then the volume of the box is going to be that value cubed, 4r cubed, which is equal to 64r cubed. So that's the volume of the box. Now the volume of the 8 spheres, we have 8 spheres, so it's going to be 8 times the volume of one sphere, which is 4/3 pi r cubed, and that gives us a volume for all of the 8 spheres of 33.51 R cubed. So porosity, therefore, for this example then, in cubic packing, is going to be the volume of the box, 64 R cubed, minus the volume of the spheres, divided by the total volume, which is 0.476, 47.6%. And as I said, this is an uppermost limit calculation. In nature, we're never going to have this high of a porosity. And the reason why, I'm going to explain a little bit later about layering and sedimentation process. But if you think of the fact that during sedimentation, this bottom layer here is laid down first, and then we have another layer that goes on top of it. If I put a layer of basketballs on the floor, I could drop basketballs probably the rest of my life, and I would never, ever make a basketball land directly on top of a basketball and stay there. It's not a stable position. What's really going to happen is the basketball is going to go in between, which is what the diagram is on the right. We call that rhombohedral packing. And so, like I said, cubic packing does not occur in nature, and it's not a natural position for particles to settle or to land. So it's more likely to fall to a more stable position in between the two. So if we want to calculate the rhombohedral packing, and I'll describe it to you, and then I would suggest that you pause and see if you can calculate the porosity of a rhombohedral packing. So if we utilize 2 layers of this system on this diagram here, if we use 2 layers to calculate it, and we think about the fact that it's still going to contain 8 spheres, but the width and depth dimension remains at 4R. But the height dimension is decreased. Instead of being 4R, the height is going to be 4R times the cosine of 45 degrees. So if you use these 3 values for width, depth, and height, pause the video and see if you can calculate the porosity for rhombohedral packing. Obviously, it has the answer there, so see if you come out with around 26%. Well, I hope you were able to calculate that. Here's the solution to the rhombohedral packing solution. So the volume of the box is going to be the width times the depth times the height. So the width and depth, both of these are 4R, but the height is 4R cosine 45 degrees. So that gives us a value of the box of 45.25 R cubed. So the volume of the 8 spheres doesn't change. So it's still going to be 8 spheres, which is 33.51 R cubed. So therefore, the porosity is going to be the volume of the box minus the volume of the spheres divided by the total volume. And there's these numbers here. And that gives us a value of about 0.26 or 26%. Now, the next concept that we're going to talk about is overburden. Very important concept. The average bulk density of all the layers of sedimentary rock containing fluids and the ocean water from the surface down to a particular depth or layer is what we call overburden. You can think of this, the way I'll illustrate it for you, a simple way is I weigh about 185 pounds. So the overburden on the bottom of my feet on my shoes is 185 pounds. So that's what I weigh. My shoes are supporting everything above them. So that's the load that my shoes have to support. So I first application exercise on overburden is to calculate the overburden of the sediments at the mud line in pounds per gallon if it's given that the porosity is about 40%. The sediments particles are not very compacted and widely spaced apart, so they are going to be about 40% at the mud line. So if we calculate the porosity, you calculate the overburden using this porosity, we have two components for our system. We have sedimentary rock, which has a specific gravity of 2.65 and 22 pounds per gallon. And the porosity is filled with 9 pound per gallon salt water, which has a specific gravity of 1.08. So overburden then is going to be the decimal volume equivalent of rock times the density of a rock plus the decimal volume of salt water times the density of salt water. So just remember that we only have two ingredients to our system, so both of these decimal equivalents have to add up to 1. So if we calculate the overburden, it's going to be 4/10 or 40% of 9 pound per gallon water, salt water, and it's going to be 6/10 of rock times 22 pounds per gallon. So that gives us a bulk density or overburden of 16.8 pounds per gallon. That's in a driller's unit. Now, overburden can be described, in other ways, such as average specific gravity. For the same example, our solution would be, if we wanted to calculate it in terms of average specific gravity, it would be 4/10 times specific gravity of 9 pound per gallon water plus 6/10 times 2.65, which is specific gravity of rock, can give us a average specific gravity of 2.02. Of course, we can go back and forth between specific gravity and pounds per gallon. If we multiply this average specific gravity of 2.02 times 8.33, which is fresh water, which has a specific gravity of 1, we get our same value back again, 16.8 pounds per gallon that we just calculated. There are no correct units. Units must be consistent. Drillers are interested in controlling the well and communicating instructions to the rig site managers. And so drillers usually calculate and work in terms of pounds per gallon of mud density. Now, reservoir engineers and geologists who are interested in reservoir volume of oil and gas prefer percent porosity. The example that we calculated is 40% porosity. Now, all wellbore information and estimates that we use in doing our well design work should be obtained by selecting the best source of information and then shifting to less reliable sources of values as necessary. And here's some examples. So, you always want to use a measured depth. Measured data, first of all, if you have a measured data point, and then if you don't have that, you may go to an empirical estimate. Now, an empirical estimate is probably going to be an equation that fits data for some area. It's not going to be, you can't derive an empirical equation. It's an equation that fits data. And then you may even make an educated guess based on experience. So some examples for overburden is you can get a direct measurement off of the density log that measures overburden. And so if you have a log on a well that you've already run a log in, you have a direct measurement there. But if you haven't drilled the well or the well's in progress, you're probably going to have to use overburden off of offset well data if you have it. And then if you don't have even an offset data point, you're going to use an empirical value that's been done based on a wide area of gathering data and make an equation that fits data. And then you may end up even making an experience estimate as a last resort. Now, pore pressure, again, We always want to use the best data and then transition to less reliable data as we have to. So a measured pore pressure could be obtained from a kick. It could be obtained in perforating a well where you use a tubing conveyed gun and you shoot the well underbalanced and then measure the pressure. It could be obtained from a production bottom hole pressure. It may be also obtained during a drill stem test. So all those could be actual measured data points. We may also just use a value of pore pressure a little bit less than mud weight. It's very common that if you drilled a well to some depth, say 13 pounds per gallon, you might assume that the pore pressure, if the well didn't kick, is a little bit less than the mud weight. If you have sand exposed, that maybe the pore pressure is about, say, 12.5 pounds per gallon. And then you can also calculate pore pressure using empirical models, and I'm going to demonstrate the Ben Eaton model for empirical equation for estimating pore pressure. And then you may also just make an experience estimate. I've had to do well designs in the past with very simple information that I had a scout ticket from an offset well, and all I knew is they had 17 pound per gallon mud at some depth. So, my experience estimate for my well was that since they had 17 pounds per gallon mud at a particular depth, then I would assume the pore pressure at that depth on my well, if I was offsetting that well, may be around 16.5 pounds per gallon. I mean, it's a lot of guesswork in this, and just using the knowledge of the information that you have. Now, fracture gradients can also be measured fracture gradients. We can use offset data of measured fracture gradients. There's empirical methods for estimating fracture gradients, which we're going to demonstrate and review today. And then you can also just make experience estimates based on doing, I call it drilling a lot of wells and setting casing at the same depth over a long history. Now, here is an empirical equation. It's just one that calculates overburden. So this equation is used. It's one that was done for the Gulf of Mexico to estimate overburden below the mudline. So this equation only estimates the overburden of the sediments below mudline. So overburden below mudline is also can be represented by the sediment gradient there, GSED, and their equation is 16.3 plus the depth below mudline divided by 3125, those in parentheses raised to the 0.6 power. Again, there are many, if you go Google papers about overburden, you'll find many papers of probably graduate students that did work, and they came up with different, I call them equations, empirical equations for modeling overburden in various areas of the world. So it always should be calibrated to specific operating areas. So these values of the exponential or the depth may change slightly in different areas of the world. Now, a linear estimate that I like to use, in fact, it's really the only one I do use because it's so simple to remember. I've already said that at the mudline, porosity is about 40% at the mudline. So, so I'm saying if you're 1 foot into the sediments, that top layer of sediments is probably around 40%. But at 5,000 feet below the mudline, you can think of as the average of the 5,000 foot layer being about 35% porosity. So that means from mudline down to 5,000 feet below the mudline, the average porosity is 35%. And then you can take that overburden, and then if you want to put it in terms of pounds per gallon using 35%, knowing that it's 35% 9 pound per gallon water and 65% rock, that 35% porosity would be the same thing as 17.5 pounds per gallon. At 10,000 feet, average porosity is about 30%, which equals 18.1 pounds per gallon. 15,000 feet from the mud line all the way down to 15,000 feet has an average porosity of about 25%, which would be about 18.7 pounds per gallon. And then likewise, between the mud line and 20,000 feet has a porosity average of about 20%, which is about 19.3 pounds per gallon. If we take a look at the, I call it a comparison of the Traugott equation to the linear. So the Traugott equation is the dash line, and the linear equation is the green line. They're not very far off, just assuming it's a linear relationship. Now, a linear relationship is not nearly good enough for geophysicists who are dealing with travel time of sound, but for drillers, you're not going to be very far off if you just used these estimates here, linear estimates for estimating, and it's easy to remember. Okay, so both of these overburden estimates are only the estimates of the sediments below the mudline. So the linear estimates correspond to the table that I've just shown you above. Porosity values in the earth really are determined indirectly from bulk density. So the values of bulk density are measured by logging tools, and then we convert a bulk density into a porosity value from the relationship that we've already shown. So just knowing that if we have a measured bulk density, we can use this relationship that if X is the percent porosity and it's filled with 9 pound per gallon fluid, then whatever the porosity value is, decimal equivalent, the remainder of the rock has to be 1 minus X, because it has to add up to 100%. Times 22 pounds per gallon equals bulk density. So an example of that would be if we have a bulk density on a well as being measured of 17.1 pounds per gallon at a particular depth in the well, what is the porosity? So if we plug these values into that equation there, and we solve for X, in this case, X comes out to be 0.377 or 37.7%. Now, since overburden is estimated based on all layers to the surface, when a location is offshore and water depth is applicable, the overburden estimate must be calculated in 2 steps. So the first step is you calculate the overburden estimate for the sediments below the mud line. So that's the first step, using the equation we've already talked about, the Traugott equation, or either using my linear relationships for calculating below the mud line. And then the arithmetic average for step 2 of the overburden below the mud line, along with the water depth and density, are used to estimate the overall overburden at a depth. So let's look at an example of that. So if I said calculate the overburden at 9,000 feet and 2,000 feet of water depth using the linear relationship for overburden below mudline. So again, I encourage you to pause this video and see if you can calculate that based on the concepts that we've already covered. Okay, the solution to this exercise number 4. So for this example, we have 2 overburden layers to consider, made up of 7,000 feet of sediments below the mud line and 2,000 feet of water depth containing 8.6 pounds per gallon seawater for a total depth of 9,000 feet. Now, since we have 7,000 foot of sediments below the mud line, we can interpolate between 5,000 feet below mud line and 10,000 feet below mud line, and therefore estimate that the porosity as being about 33% from the table. This means that the average porosity of all of the sediments below the mudline is 33%, between 0 and 7,000 feet below mudline. It does not mean that the porosity at 7,000 feet below mudline is 33%. It means the average between the mudline and 7,000 feet is 33%. So therefore, in step 1, we calculate the overburden below mudline. So it's going to be 0.33 times it's filled with 9 pounds per gallon water, plus the remainder is rock, 0.67 times 22. So the overburden below mudline would be 17.7 pounds per gallon. And then in step 2, we take the arithmetic average of these two layers. So for this example, we have an overburden of 17.7 of the sediments below mudline times the thickness, which is 7,000 feet, plus 8.6 seawater times 2,000 feet, then dividing by the total depth of 9,000 feet gives us an overall overburden of 15.7 pounds per gallon. So you can see on this example, going from a overburden below mudline of 17.7 down to 15.7, there's a great reduction from this 2,000 feet of water, bringing the arithmetic average down. Now, salt has a specific gravity of 2.15, which is the equivalent of 17.9 pounds per gallon, which I have already shown, and it can have a significant effect upon overburden estimates as well. Here's just a diagram that I did using very shallow water, calculating the overburden on very, very shallow water, which would be the red line curve, and then using 5,000 foot water depth, which is the green line, it would be this curve if you follow the overburden down for that one. And then if you have 10,000 feet of salt, which I've shown here, and you calculate using the reduced weight of the salt layer, it can bring the overburden down at the bottom about 0.5 pound per gallon less than the overburden from not having salt. So salt can have a big effect as well. It has to be taken into consideration when you have very, very thick salt sections. Now, next concept is extremely important, is pressure. Pressure is force acting over a cross-sectional area. Pressure can be thought of in several ways. For solids, we generally think of pressure in terms of stress as force divided by area, and normally the units are pounds per square inch of stress. Now, pressure from a fluid is unique that it acts in all directions. So hydrostatic pressure is a pressure resulting from the gravitational force. So the direction of gravity is always acting towards the center of the Earth. So any length or depth measurement must be the component of the length towards the center of the Earth, as shown in the diagram below. So we normally use true vertical depth in the drilling world as the length of the well bore that is acting in the direction of gravity. So gravity is acting toward the center of the Earth. And so if we have a directional well, an inclined well bore with a measured length, we only use the component that's in the direction towards the center of the Earth in calculating pressure. So very important concept when we're calculating any type of pressure. Now, as I've said, pressure is equal to force over area. And when we're working in the Earth in a gravitational field, we can also think of it as being weight divided by the area. So I've drawn for illustration purposes here a cubed, which is a cubic foot. Each dimension is 1 foot. Its width, depth, and height is 1 foot. And we can measure pressure in many different units. We can sometimes, for construction, they will measure pressure in terms of pounds per square foot, or maybe tons per square foot. So you'll design components based on tons per square foot as a pressure. But normally in our drilling world, we use pounds per square inch. So I'll just illustrate where the value comes from for us to calculate pressure in pounds per square inch. So a cubic foot, just a given, is equal to 7.48 gallons. So this cubic foot is 7.48 gallons. It happens to have an area on the bottom, which is the dimensions of 12 inches by 12 inches. So that would give us an area on the bottom of the cube of 12 times 12, or 144 square inches. Now, since we're dealing with pressure in PSI, what I have done is taken just portion of this cube, and I've constructed a 1 foot tall section of this and column, which is 1 square inch by 1 foot tall. So if I want to calculate what is this volume that is 1 square inch and 1 foot tall, then it's going to be 7.48 gallons total divided by 144 square inches, because I'm only interested in 1 square inch, and that would give this volume 0.052 gallons per square inch foot, 1 foot tall. So that's where the 0.052 comes from, that we use all the time in our drilling world for calculating pressures. So the pressure is force divided by area, which is also can be thought of as the weight of the fluid in a column, in that square inch column in PSI per square inch. So using the column with 1 square inch cross section and 1 foot tall with a volume of 0.052 gallons per square inch foot, then we can calculate the pressure for a column that's any height and in any density of fluid. The pressure will then be the weight of the fluid density, like pounds per gallon, in a 1 square inch column, however tall it is in TBD feet. So it's going to give us the pressure equation is weight divided by area, and our area is 1 square inch. Going to be 0.052 gallons per inch squared foot times the TBD height in feet times the density in pounds per gallon will give us the PSI pressure. Now, pore pressure is the pressure within the pore spaces of the rocks within the earth. Pore pressures are obtained from the best source of information to the least reliable source of information. So it's always best, as I've described previously, to use actual pressures if you have them, which could come from kicks, drill stem test, offset wells, perforating a well, bottom hole pressure measurements, or other sources. Or you could also, you may assume that the drilling mud weight density is close to the pore pressure. I've had to do that a lot of times. So you use offset well information, and like I say, if the mud weight was 14 pounds per gallon, you might assume that the drillers did a pretty good job of staying close with the mud weight, and the pore pressure is just a little bit less, maybe 13.5 pounds per gallon. And then we can use an empirical method, a pore pressure plot using resistivity. Now, very important to note that this empirical method only works well in a continuous depositional basin environment outboard of continents containing sand and shale layering. So it only works if you have sand and shale layering outboard of a continent, which would be like a downstream of the Mississippi River system, something like that. It could be in other continents as well. So I'm just going to illustrate how we can do pore pressure plots using the Den Eaton method for predicting pore pressure. So when you use this methodology for predicting pore pressure, what you do is you plot up the resistivity in shale formations. You only use the shale values, and that gives you these dark spots that I've plotted up here to represent the actual shale values on a well off of a resistivity log on an offset well. Now, what you do in estimating pore pressure is that you draw a best fit line through what we would call the normal pressure data that you have, and then you pick values of R normal is what we would expect the resistivity to be at these deeper depths, but the actual resistivity are these values. Now, the reason these values decrease it absolutely makes sense when you think about the fact that as we go deeper and deeper in the earth, porosity is decreasing. So if porosity is decreasing, that means as we go deeper, there's a lesser and lesser amount of salt water in the pore spaces. So salt water conducts electricity very well. And so if we have a lesser amount of salt water in the pore spaces, it is going to have a tendency to make this resistivity increase. So that's why this concept works. It's a natural way of working, and Dr. Ben Eaton did work on this a long time ago, I think in the late 1950s, I believe, and wrote papers on this methodology. And it works pretty well with practice and using it over and over in the same basins. I've used it a lot for wells all along the Gulf Coast, in the Gulf of Mexico, and it works pretty well, gives you good qualitative answers, not necessarily absolute, but useful for planning drilling wells. And here's the equation for using the Ben Eaton. It's an empirical equation. You can't derive it. He just used this methodology a lot, using a lot of logs, and where he had good information on the wells, where he knew what the pressures were because they had been perforated, or he got information from bottom hole pressure measurements or whatever, he back calculated an equation that fit data. So that's how he came up with this methodology, and it works pretty good. So the value of normal pressure that you use in this equation, again, is the 9 pounds per gallon, which again is about the average, I call it gradient of salt water in the pore spaces because of the increased temperature and salinity of salt. All right. Now, sand and shale layering takes place in a continuous depositional basin environment similar to the Gulf of Mexico, in which all sediments are deposited downstream from the mouth of a river system like the Mississippi River. The layering is caused by very long climatic weather changes in rainfall, velocity, and energy to move particles. So I'm going to kind of illustrate that. So when you have periods of let's say very little rainfall, you may go, I'm making stories up here, 100,000 years with very little rainfall on the continent of the United States. Well, when that occurs, if you think about the two substances I described, clay particles and sand particles, so during a period of time that you have very little energy, the only particles that could move would be like clay particles. Clay particles are very similar to this coin, which is very thin, so its cross-sectional area compared to its weight is very high. And so it would take very little energy to move a particle of clay. You can think of it as a clay particle as sort of being like a feather, whereas a particle of sand is going to be similar to like this marble. Its cross-sectional area is not nearly as high compared to its weight. So when you have low periods of energy, not much rainfall, then when there's plenty of energy within the Mississippi River to bring both of these particles down to the mouth of the river. But what's going to happen is that the sand particles, when you get to a very low velocity out in the Gulf of Mexico, are going to fall out. So it's going to fall out at the mouth of the river and settle out there for 100,000 years or whatever during this low energy period. And then you're going to have another climactic weather condition where you have very, very high rainfall. So then you have extremely high velocities coming down the Mississippi River, and it's going to pick up a big pile of sand and make a big sand layer go out over a very large area of the clay that was deposited under it. And so this cycles of low energy in which only clay can be deposited, and then high energy where you get this big layering of sand on top of the clay is what causes the sand shale layerings that we have. Now, I want to illustrate something here on this diagram that I've kind of drawn. In general, down to some point in the Earth, we will think of it as the Earth is normal pressure. So if we have communication down to some depth in the Earth, it might be around this depth here, where all the pore spaces can communicate back up to the surface. All the pressures are going to be close to 9 pounds per gallon. And the way I think of that is this. So if I have a bottle here, and if I loosen the top on this bottle, then the pressure on the bottom of this bottle is hydrostatic of this fluid back up to the surface. So if we want to calculate the bottom hole pressure, in this case, the bottom hole pressure is going to be the hydrostatic only of this fluid. So if I had 9 pound per gallon fluid in this bottle, it would represent this rock in which is equal to 9 pounds per gallon because it's communicating back to the surface and able to relieve itself if this top is loose. So if I squeeze the top of this bottle with the top loose, the pressure is not going to increase on this bottle. The pressure at the bottom, as long as it's loose and can equalize with the top, it's never increasing. However, geology is a little bit complicated and can be complicated, and we can have earth movements such that if I tighten the top on this bottle so no fluid can escape, that's what's represented down below this section, in which I've had some movements, mass movements of earth, which has caused some faulting. And now this rock below this point here does not have communication back up to the surface. So it's no longer communicated. And so if I squeeze the bottle with the top closed in, it's going to increase pressure. So I'm going to have a higher pressure on the bottom of the bottle due to the hydrostatic pressure in the bottle, plus the pressure I induce because I'm squeezing the bottle. So that's an abnormal pressure due to compaction that's going to have a tendency to squeeze that bottle. Now, for this drawing that I try to illustrate the way nature works, in this case, we're probably going to have two transitions on this well. So you're probably going to have a transition to go from normal pressure along in here somewhere to a higher pressure through this section of rock. Now, I call it the relief valve for this section of rock is probably going to be the top of where these two faults go. So if the top of these two faults have a fracture gradient of, say, 14.5 pounds per gallon, then you may drill all the way down to here with around 9 to 9.5 pounds per gallon mud, and then you may have to drill through this section below these two sands with maybe around 14.5 to 15 pounds per gallon. And then you will see on my diagram that I've made that you have a deeper sand section here that it looks like it may not be communicated with these sands above it. And if these fracture gradients of these shales above this rock section is say 16.5 pounds per gallon, then we may need to drill through this section with 14.5 pounds per gallon, and then increase, have a secondary transition, and then drill through the second sand section or series with the higher mud weight, maybe around 16.5 pounds per gallon. So pressure is going to occur based on nature and geology. I mean, it's not just somebody putting a number on a piece of paper. It's happening because of the geology taking place. And here's the illustration that I described about the sand particle being sort of like the marble, and that the clay particle is sort of like you can think of it as like a dime I used. It's like a feather. So the dime or the feather can move with very little energy, takes very little energy to move it, and the sand particle, which has a very low surface area compared to its weight, is hard to move, and it will only move and have layers of sand when you have periods of high energy. Now, the significance of this is being able to apply it. So I want to describe that everything related to well design and risk management of a well is predicated upon having a good understanding of our drilling environment. So before you do any well design planning at all, you need to have a good understanding of your drilling environment. I mean, we cannot imagine a civil engineer designing a building and building a skyscraper without any knowledge of not understanding of what his soils are that's supporting his building. There's nothing any more important than understanding your environment that you're dealing with. So we need to know our drilling environment in order to choose casing setting depths and the number of strings that's going to be required, to do well control evaluation and analysis, to do barrier testing and evaluation, to determine our casing pressure loads and casing design, as well as hole cleaning analysis. So the way it works is the very first thing we calculate, and that was the very first thing that I reviewed, was overburden. So we start off calculating overburden, and then from the equation that you saw with Ben Eaton, we use overburden to estimate pore pressure. So you notice that overburden was a requirement in Ben Eaton's equation for estimating pore pressure. So we first start off calculating overburden. We use overburden to calculate pore pressure. And then we use both of these, overburden and pore pressure, to estimate fracture gradient. So on our well, I call them the limits of our well is pore pressure is the pressure we need to control the well, and we're going to have a mud weight greater than pore pressure. And fracture pressure is going to be a value in between overburden and pore pressure. So we're going to estimate fracture pressure. So we need all three of these values to have a good understanding of our drilling environment. So we calculate overburden first, used overburden to estimate pore pressure, and then last step is we use overburden and pore pressure to estimate fracture gradient. Now, fracture pressure is the lowest natural stress in the rock formation, in which, if exceeded, the formation is likely to fail. There are two horizontal stresses which have a lower stress value than the one vertical stress, which equals overburden. So we need to know fracture pressure so that we can complete a well-bore fracture gradient model for our well. This is very critical. We use this model to do our well design from. You don't start doing a well design until you have an understanding of your drilling environment. So we've already talked about calculating overburden, how we can estimate overburden. Then we can use the best method that we have available to estimate pore pressures, and then using the overburden and pore pressure, we will estimate values of sand and shale fracture gradients. So that's where we're headed next. It's estimating fracture pressures. We cannot measure or estimate horizontal stresses directly. So we must first estimate the maximum stress, which is overburden, and then use relationships to estimate the horizontal stresses. So I've drawn a cube here that shows the overburden on it, which is the vertical stress here on the diagram. And I've also shown two horizontal stresses. So a vertical load, which is the overburden, is going to induce a horizontal stress in the formation rock. So we can think of it based on this diagram here, that if I put and it doesn't really matter what you think of in terms of cubic inches or cubic feet of rock, that if I put a vertical load on a block, a cube of earth, it's going to have a tendency to become a little shorter in height, and it's going to have a tendency to become a little wider. So this term for this change that takes place from this vertical load, causing it to get wider and shorter, is Poisson's ratio. So Poisson's ratio is the change in the width, or change in the strain in the width, divided by the change in the strain in the height. So that's what Poisson's ratio is. You see here listed. That's just a principle of materials. So an increase in Poisson's ratio results in a greater horizontal stress. So if we have a higher Poisson's ratio material, that means this is going to have a tendency to get wider and induce a stress of one block pushing against another block. So you got to think about that if I've got a block of rock here, that block is against another block right beside it, and they're going to be pushing against each other, inducing a horizontal stress. Now here are some Poisson's ratios of common materials. I'm not going to read these out to you, but you can see that they range from quartz being a value of about 0.17 to the materials I've listed of rubber being 0.5. So it's rubber. If I squish rubber, it's going to have a tendency to really push out to the side if I squish rubber with a vertical load. So overburden is the vertical stress at any depth of interest, which is holding up every other layer above it. We've talked about this, what overburden means. And overburden can be considered to be made up of two components or forces equaling to the weight of the layers above. I've already said that pressure is always acting in all directions of a fluid. So we always have the pressure of the rock formation fluids acting in all directions. So that pressure is always helping to hold up any layers above any depth in the earth. And then we have the effective stress. So effective stress, sometimes it's referred to as matrix stress, as the stress of the rock particles pressing against one another. We don't measure effective stress directly, but we subtract pore pressure from overburden to obtain effective stress. So, if you think about it, that the overburden is, let's say, 18 pounds per gallon, and it has a 9 pound per gallon pressure, that means the effective stress would be 9, because those two numbers have to equal overburden. So the effective stress would be 9 and the pore pressure would be 9, and the earth is happy. Okay, so overburden is effective stress plus pore pressure, that combination. So then we can use this same relationship, plug back in here, and see that overburden is equal to overburden minus pore pressure plus pore pressure. So fracture pressure is effective stress times some rock stress coefficient plus pore pressure. So in other words, as we compress a value of rock based on the material properties of that rock, portion of that matrix stress is going to contribute to inducing a horizontal stress. And so that contribution of that matrix stress in a horizontal direction, along with the pressure that exists at that depth, is going to be the fracture pressure. So those two stresses added together equals the fracture pressure. So the fracture pressure equation that we use is going to be overburden minus pore pressure times a rock stress coefficient, that gives us the horizontal stress due to the matrix stress, plus adding back the pore pressure back in. So pore pressure is always acting in all directions. So then the final equation we use for calculating fracture pressure, then it's overburden minus pore pressure times this stress coefficient, which we call K, and then adding back in the pore pressure again. Now, the stress coefficient varies with materials. So if I use the quartz that I used before for a pure substance, the stress coefficient is going to be the Poisson's ratio divided by 1 minus Poisson's ratio for a pure substance. You can derive that. I won't do it today. And see that's equal to the stress coefficient. So the stress coefficient for pure quartz, which the example that I used in the porosity was quartz, would be has a Poisson's ratio of 0.17, and so the stress coefficient is going to be 0.17 divided by 1 minus 0.7 would give us a stress coefficient of about 0.205. All right. Now, it's very important to know that rock formation is not a pure substance. It contains a varying amount of void spaces based on the porosity estimation. So since oil field use, we are not drilling pure materials, we must use a modified value of stress coefficient in order to estimate our fracture gradients. We're never drilling any kind of pure substance. We're drilling, you can think of it as we're drilling through sponge. It's a sponge of sands or it's a sponge of shale. It all contains, water porosity. Even in the shale, it has porosity. Now, these are my own personal observations that I came up with in around the 1980s, early in my career. Dr. Ben Eaton had developed a methodology for estimating shoe strength values using the fracture pressure equation that I've already shown and using the shale material properties. There was, at the time, there wasn't a strong industry understanding or consideration at the time for alternate sources of estimating doing well design work other than using shoe strength. But what I observed early on in my career was that, and this happened, I'm saying a lot of times, I collected a lot of data, but for intermediate casing shoes that are approximately, say, 10 to 12,000 foot TVD, they were tested to equivalent mud weights of, say, in the range of 16.7 pounds per gallon. And then when I drilled down below that casing section, below the intermediate casing, returns were lost below the casing shoes when mud weight was increased between 14.5 and 15 pounds per gallon. So you got to say, what's wrong? It's something wrong here going on. So then I also had observed that I tested casing shoes at, say 4,000 feet to 14.5 pounds per gallon, and then I lost returns down below these casing shoes when the mud was weighted up to, say, 13 pounds per gallon. So these observations, made me realize, or come to the conclusion, that the material differences between sands and shales have a substantial difference relating to fracture pressure. So over a long number of years, I collected hundreds of fracture gradient data points between 4,000 feet TBD and around 15,000 feet TBD after mud returns were lost. I also worked with depleted sands in many old fields, so I drilled into depleted sands, lost returns, so I knew what the pore pressure was. And so I did this over and over, and I back calculated stress coefficient values. So it's pretty easy to estimate overburden. And so in the cases where I got data and I measured fracture pressures because I lost returns, filled a hole up, so I knew, and I knew what the pore pressure was at a depth where I lost returns, or where the returns were lost right below a casing shoe, then I was able to back calculate values of stress coefficient that fit my data. So remember, I may have set casing at 10,000 feet, and at 10,050 feet, there's a sand. Then when I got to 12,000 feet, I weighted up my mud to 14.5 pounds per gallon, and I lost returns. Remember, I did not lose returns at 12,000 feet. I lost returns in that sand that's at 10,050 feet. I know what the pore pressure was at 10,050 feet. I know what the overburden is at 10,050 feet. I measured the fracture pressure, and I back calculated the stress coefficient that fit my conditions. So doing this hundreds of times, the best conclusion that I came up with on all of my data over a long number of years was use a stress coefficient for shale of 0.7 and to use a stress coefficient for sands of 0.47. Now, this data was collected in the Gulf Coast area of the United States and the Gulf of Mexico. So that's the only place I collected my data. And if you go to other places in the world, you probably should do the same thing I did, is calibrate your information to the areas where you operate. So again, for a pure substance, stress coefficient is Poisson's ratio divided by 1 minus Poisson's ratio. So, if you use this relationship for stress coefficient being Poisson's ratio over 1 minus Poisson's ratio, we can calculate a pseudo, how could you call it, ratio for shale would be 0.41, and a pseudo Poisson's ratio for sands would be 0.32, just solving for using a stress coefficient of 0.7 and a stress coefficient of 0.47 for sands. You'll back calculate these values of Poisson's ratio. But remember, these are Poisson's ratio for a sponge, not a pure substance. So again, I've listed these values here. Very important. If you're planting wells in the Gulf of Mexico area, I think they will probably serve you pretty well. But always do your best to calibrate and as best you can, get your best information you can on your operating area. So let's take a look at the observation example that happened to me. If we assess the observation below the intermediate casing shoe that I just described, and I say it have an estimated pore pressure of 11.5 pounds per gallon, using the average porosity of 30% at 10,000 feet in very shallow water, overburden is going to be 0.3 times 9 pounds per gallon water, plus 7/10 times 22, which is rock. That's going to give us an overburden of 18.1 pounds per gallon. Of course, you can also get it off the graph on page 7, no right way, just it's easy to calculate. So the shale fracture gradient is going to be overburden minus pore pressure times using the stress coefficient of shale, which is 0.7, plus the pore pressure. And that's going to equal to 18.1 minus 11.5, the difference between those numbers, times 0.7 plus the pore pressure of 11.5, and that gives us a value of 16.1, which is, again, is close to the observed shoe test I got for that depth of, say between 16 and 17 pounds per gallon. Now the estimated sand fracture pressure using the fracture pressure equation and the stress coefficient for sand of 0.47, we get the following estimate. So the sand fracture gradient estimate would be, the overburden on this pore pressure times 0.47 plus the pore pressure. So for this example, it's going to be the overburden of 18.1 minus the pore pressure of 11.5. You take the difference between those values, multiply it times the sand stress coefficient, which is 0.47, plus the pore pressure of 11.5, gives us a sand fracture gradient value of 14.6. Guess what? That's the same value that I ended up with after I lost returns and filled my hole up with seawater. I came up with this kind of fracture pressure. And of course, when I say this, there's nothing wrong. Again, I hope you realize that it's really obvious from this exercise, if you believe this, that basing your I call it well integrity or your well control based on a shoe is a very flawed, I call it example. So calibration of this stress coefficient value in an operating area should be done for better estimating of fracture pressures. So the way I like to describe this, it may not be a very good way, but I like to think of it that way, is that if you're operating, if you're going to climb down off of a tall building and it's on fire and you've got a rope that's like this piece of rope that I've got here in my hand, that your very long rope in the middle of it has a little bitty piece of rope. And I'm going to climb down off the side of a burning building. Which piece of rope am I going to be concerned about if I'm climbing down that building? The big rope that has a very high tensile strength, or the small piece of rope that is going to be the one that fails and I'm going to drop to the ground? So, you need to understand your rock strength for making good drilling decisions. Okay, so assessing that is very important. Now, this is a graph that I've already described. We want to ending with a borehole fracture gradient model for our well. And before you start any well design, you want to have a good understanding of your I call it your pore pressure, which is the red line, your overburden, which is this brownish line, your sand fracture gradient, which is the green line, and then your shale fracture gradient. Now, in determining, I'm just going to illustrate it on this diagram here, when you're planning casing setting depths, if you look at the casing string, the surface casing string that I have placed here on this particular model, about 5,500 feet, you'll see that it has a shale fracture gradient that's a little bit less than 14 pounds per gallon, but it has a sand fracture gradient of about 12.5 pounds per gallon, which again matches up to what I observed, that many times I would set surface casing shoes at 4,000 feet or 4,500 feet, get a 14.5 pound shoe test, and then I would lose returns when I weighted my mud up. This is the reason. The sand fracture gradient, when you look at this borehole fracture gradient model, is about 1.5 pounds per gallon less for the sand than it is for the shale at the same depth. So based on this model, to make sure you don't lose returns, you're not going to be able to drill any farther than your mud weight is based on this sand fracture gradient. So if this sand fracture gradient is 12.5 pounds per gallon, I'm only going to be able to drill down to the point at which my mud weight gets around 12 to 12.5 pounds per gallon. So for this illustration, I'm going to have to stop drilling when I'm at 12,000 feet and I've got, say, around 12.5 pound per gallon mud, because that is all this sand at the casing shoe is going to stand. Likewise, if I set casing at 12,000 feet, the sand fracture gradient now is about 14.6 pounds per gallon. And for that next whole section, I'm only going to be able to drill that looking up, my mud weight cannot exceed about 14.6 pounds per gallon. And I'm going to have to set casing string again. And likewise, I do this again, and I do this again. So you have to set casing strings to mitigate loss returns based on the sand fracture gradient. Okay, very important concept. So a well design based solely on a shoe test is a flawed design, because you may set the casing shoe in the very strongest rock, but 50 feet below that very strong rock, you have this very weak rock that is going to fracture and cause you to lose returns. Now, this is a very important principle here that I've got listed. Your actual casing setting depths may be adjusted based on your knowledge of the absence or presence of sand formations. So if you know, let's just use as an example. Let's just say for this example that I set casing at 12,000 feet here. Based on this model, it shows that the sand fracture gradient is 14.5 pounds per gallon. But if you have knowledge on your well that between 12,000 feet and 14,000 feet, there are no sands, you have absolute knowledge of that, you can ignore this green line. You can take a pencil, if you want to, and an eraser, and erase that line if you wanted to. You can think of it that way. It only has meaning if you have sands in that interval. But if you don't have sands, you can adjust your casing setting depths based on that knowledge. The fracture gradient curve for sands does not apply if there are no sands present. That's what I mean. So the real well-designed challenge is to wrestle with the question of how much do I really know about the geology and willing to accept the consequences, because nature is going to do its thing based on what's there. So the two principles that we use in well design are in choosing casing setting depths and mitigating loss returns. You choose casing setting depths based on the sand fracture gradient curve to avoid losing returns. I've already described that. But yet, on the other hand, when we're doing casing design load analysis, it's done using only the shale fracture gradient curve, which will provide us the most robust casing design loads. We want the highest robust loads to protect people and the environment. So if you ask any engineer what's the main task that you have, and that is to protect people and the environment, you always have to remember there may be no sands present below a particular casing shoe. You may know from offset wells and think there's going to be several sands below a casing shoe, but in the real world, you may drill out and they may be faulted out and there are no sands in a section that you thought was going to be some sands. All right. Now, based on everything I've described and all the concepts, I would suggest that you pause and take a look at the introductory exercise that I suggested at the beginning of this video, and see if you can estimate the shale and the sand fracture gradients on the exercise of the introductory question as we began this video. So please pause and calculate your introductory exercise, sand and shale fracture gradients. Okay, here's this, again, I've listed again in the notes here, the introductory questions that I ask. for a well being planned in the Gulf of Mexico with no near surface salt, what would be the estimated shoe fracture gradient in a shell formation at 10,000 feet on a well being planned in 7,000 foot water depth, in which the expected formation pore pressure is 9.5 pounds per gallon. And then I say, if the sand is present 50 feet below the casing shoe in the same pore pressure environment, what would be the expected sand fracture gradient? So, like I say, if you were planning on drilling a well, this particular well, and this is the depth that you're considering setting a casing string on, you should know what the sand and shell fracture gradients are so that you can do well control assessments and have an idea of what kind of mud weight you can use below these casing shoes. So it's a very important question to know to understand your earth estimates. So the solution for this is based on the information given. The depth of interest is 3,000 feet below the mud line, based on 10,000 foot depth minus the water depth of 7,000 feet. So using the table that we've already seen and interpolating between 40% at the mud line and 35% at 5,000 feet below mud line, we would estimate that the average porosity 3,000 feet below mud line to be about 37%. So it's just interpolating between those two values. So using 37% porosity for 3,000 feet below mud line, we can calculate the overburden of the sediments below mud line. So the overburden of the sediments below mud line are going to be the 37% 9 pound per gallon water and 63% rock, which is shown here. So the overburden of the below mud line is 0.37 times 9 pound per gallon salt water plus 63% rock, which is 22 pounds per gallon, and that gives us an overburden of the sediments of 17.2 pounds per gallon. And so the overburden at 10,000 feet can be determined by, on the second step, taking the arithmetic average between the two layers of 7,000 foot of water depth that has 8.6 pounds per gallon and the 3,000 foot of sediments, which has an average density of 17.2 pounds per gallon. So if we take this arithmetic average, 7,000 times 8.6 plus 3,000 foot of sediments at 17.2 pounds per gallon divided by the total depth of 10,000 feet gives us an overall overburden of 10,000 feet of 11.2 pounds per gallon. And then using the stress coefficients for shale and sand that I've already described, we can calculate the shale fracture gradient as being the overburden we just calculated, 11.2 pounds per gallon, minus the pore pressure of 9.5 pounds per gallon, taking that difference, multiplying it times the stress coefficient of shale, which is 0.7, adding it to the pore pressure, and that gives us a shale fracture gradient of 10.7 pounds per gallon. And then the sand fracture gradient, likewise, we take the difference between the effective stress, which is overburden, minus pore pressure, times the stress coefficient for sand, which is 0.47, add it back to the pore pressure, and that gives us this value here, 11.2 of overburden minus 9.5 pore pressure times the stress coefficient of 0.47, adding it back to the pore pressure of 9.5 gives us a sand fracture gradient of 10.3 pounds per gallon. So the way you use these numbers is you use this number, this 10.3 pound per gallon number is kind of your weak spot near the shoe. So that's going to be kind of your limiting factor from well control standpoint. It's going to be the limiting factor of your maximum mud weight that you can use in that next whole section. So that's the way you would use that information. Very important. All right. I'm going to end this with a, just to kind of sum up this whole concept, how important understanding these concepts are. There's a lot of things happen in this industry that is because people don't assess their environment before they make decisions. They just copy and paste information or use a number that someone else gave them without considering what do I know now? Does it seem reasonable? So here's my, I call it final question scenario that we're going to review. I hope kind of brings home the importance of understanding overburden, pore pressure, and fracture gradients. So plans are made to deepen a well to 12,000 feet located in the marsh of South Louisiana in a canal which has 9 5/8 casing set at 10,000 feet. It was drilled to this depth with 10.5 pounds per gallon mud, and it was planned that the open hole section is to be drilled with 13 pounds per gallon mud below it. I guess someone thought that there's going to be a pressure increase based on offset information. The barge rig is moved onto the location, and the well is successfully drilled to 12,000 feet, only requiring 10.5 pounds per gallon mud, as no pressure transition was detected after drilling out the casing chute. A 7-inch liner is successfully run and cemented using 35% excess slurry with a 300-foot liner lap up to 9,700 feet. The drill pipe is pulled out of the hole after running the liner, and then the well is cleaned out to the top of the liner at 9,700 feet with a bit, encountering ratty cement at 9,350 feet, and then very hard cement on top of the liner. The rig follows the completion procedure written at the beginning of the project to test the liner lap by pressuring up on top of the liner to 2,100 psi, and no leak off in pressure occurs. It's holding very well. A lot of times we call it holding like a jug. Since the liner lap test is successful, the rig then begins a displacement process to displace out the 10.5 pound per gallon mud from the well with canal water prior to displacing the well over 10.5 pounds per gallon brine completion fluid. About halfway through the displacement process with the canal water, which would weigh, maybe, it's close to fresh water, 8.3 or 8.6 pounds per gallon, the well begins to unload, and the well is successfully shut in with 2,700 psi of casing pressure. The rig makes preparations to circulate out the well, and once circulation begins on the choke, the casing pressure drops to 0, and it is found that the drill string is stuck and packed off from solids with no ability to circulate. What is the likely cause of this very difficult situation? I would encourage you to pause the video now and see if you can assess what you think happened in this scenario, and then we will take a look at it. If we take a look at the scenario that occurred based on this description, we will find that it may not actually surprise us of what occurred. If we estimate the overburden at 10,000 feet using a 30% average porosity, we'll get the overburden of 0.3 times 9 pounds per gallon plus 7/10 times 22 equals 18.1 pounds per gallon. And if we assume the pore pressure is about 0.5 pound per gallon less than the mud weight, then we would assume at that depth that the pore pressure would be about 10 pounds per gallon. And then if we use 10 pounds per gallon as the pore pressure and estimate the 9 5/8 shoe fracture gradient in a shell, then the estimate of the fracture pressure would be 18.1, which is the overburden, minus the pore pressure of 10 pounds per gallon, times the shell stress coefficient of 0.7, plus the 10 pounds per gallon equals 15.7 pounds per gallon. But if we take a look at what we actually did during the operations in our barrier test, we tested the barrier to 2,100 pounds over 10.5 pounds per gallon mud. So the equivalent mud weight would be the equivalent mud weight of the pressure, which would be 2,100 pounds divided by 0.052 divided by 10,000 feet, plus the mud weight that was in the well, which was 10.5 pounds per gallon, which would give us an overall equivalent mud weight during the barrier test of 14.5 pounds per gallon. So in this case, the fracture gradient is greater than the equivalent mud weight of the barrier test by actually about 1.2 pounds per gallon. So if I ask the question, what was accomplished with the liner lap barrier test, and the correct answer would be absolutely nothing. The well actually may have held 2,100 psi over the 10.5 pound per gallon mud had it not even been cemented. If the fracture gradient is 15.7 and you only tested to an equivalent of 14.5, then whether you had even cemented a well or not, it may have held that as it did during what they thought was a right barrier test. So the mistake that was made was not recognizing. Somebody just operates off of a piece of paper that says test to 2,100 pounds, but nobody really analyzes what has occurred or changed. The original procedure was that they were going to drill this well with 13 pound per gallon mud, and if you'd add 4 pounds per gallon equivalent mud weight from the pressure plus 13 pound per gallon mud, this number would have been a 17 pound per gallon equivalent test, barrier test. But by the fact that they did not weight the mud up, their equivalent test they did was less than the fracture gradient. So they actually did not accomplish anything doing the barrier test. So that's a very important concept, is that anytime you're going to test a barrier, you've got to test to a pressure above the strength of the formation that you're testing against if you want to accomplish a barrier test. So the bottom line is that you always want to assess and understand your drilling environment in making all drilling decisions. So I hope that you have found this video very informative for you. Tried to review not only overburden, pore pressure, and fracture gradients, but also how to calculate those values such that you can use these values and make good drilling decisions. It's not just good enough to say, I've heard of fracture gradients, so therefore I know what fracture gradients are. That's not good enough. You have to be able to assess your environment to know what the value is based on your particular circumstances so that you can make very good drilling decisions in well design and execution. It's been my pleasure to present this material to you, and good luck in your drilling operations.